Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HRF, Lesson 10, Filters. In this lesson, we'll learn how digital filters work, and we'll learn a little bit about analog filters. In the Lesson 9 homework, I asked you to create a flow graph that looks like this. It has a noise source, throttled, and visualized with a WX GUI FFT sync. I set the sample rate to 1 million samples per second. Let's see what this looks like. This shows us the frequency domain representation of the noise. And what we're seeing here is that there's some of every frequency present in noise. If we hit the average button, we can see that it's pretty flat. And if we averaged over a longer period of time, we probably see that it's even more flat than that. Every frequency is present in random noise. Now, this is a useful way to visualize the frequency response of a filter. Normally, a filter is something that changes the frequency, how much of each frequency is present in a signal. And by starting with a signal that has every frequency present, we can compare the results of different filters against each other. Let's see what we get here if we install a filter. And I'll use a low-pass filter. I think that's the first one I asked you to try. We'll put it here between the throttle and the FFT sync. And it wants us to specify a cutoff frequency and a transition width. Now I like to specify these with sliders. So I go into instrumentation, no, not instrumentation, GUI widgets, WX GUI slider. And I'll create one that I call cutoff, and give it a default value. I think I suggested samp_rate divided by 8, a minimum of samp_rate divided by 1,000. I just want it to be something close to 0, but not actually 0. And a maximum of samp_rate over 2. I'll give it a number of steps, 1,000. And then I can take that cutoff and put it in the cutoff frequency parameter of my low-pass filter. And now it's happier than it was before, but it still wants a transition width. So I'm going to copy and paste and create a new slider with the same characteristics called transition. And then I'll set my transition width here to transition. And let's see how things look. Now this looks a little bit different. And if I use my average button, I can see very clearly what the frequency response of this low-pass filter is. It's a low-pass filter, which means it passes frequencies that are low or that are closer to 0 hertz. But frequencies that are high, that are far away from 0 hertz, are blocked. They're reduced by many dB. And if you adjust the transition width, if I make the transition width narrower, you can see that it takes a little time for this averaging to catch up, but you can see that it has a flat response through this, what's called the pass band, up until the cutoff frequency at 125 kilohertz, also at negative 125 kilohertz. And then there's this shoulder, there's this transition where it goes from the pass band to the stop band. And the width of that shoulder is called the transition width. If I make the transition width a little wider, you can see that my pass band in the middle here doesn't change much at all, but this section between the pass band and the stop band, which is everything outside of the pass band, that transition has widened. If I adjust my cutoff, I can make my filter wider, or I can make it narrower. If I make it very narrow, I might want to also have a narrow transition width. And you can see that very easily in GNU Radio, I can create a low-pass filter and configure it to have whatever pass band I want and however much transition width I want. Now, one thing I asked you to do was to take a look at what happens when you adjust these sliders. Take a look at what happens to your CPU utilization. So I will bring up a window here and run htop, which is my favorite way to visualize CPU utilization, you can see that right now I'm using 30% or so of my CPU. I have 4 cores here, and they're all moderately utilized. And if I increase my transition width a bunch, not much changes. But if I decrease it a bunch, if I make it really quite narrow, I can go smaller and smaller. And as I get really close to 0, you might see things change a little bit. So you see how much more CPU I'm using now? As I go even closer to 0, look at that. I'm way down at 1 kilohertz transition width. That's only 1,000th of my sample rate. And I'm using about twice as much CPU power to do that. Now I have this beautiful looking filter. It has a very sharp transition. Frequencies that I want are passed through. Frequencies that I don't want are blocked, and there's a dramatic cutoff from one part of the edge to the other, past the edge. But it comes at an expense. If I soften my edges a little bit, then I use a lot less CPU time. And in this lesson, we'll explore why that is. Now, I'd like to do a little demonstration for you. I'll stop this flow graph and start a new one. And I'd like to show you what happens if I take a noise source. I'll start out in the same way as the previous flow graph. I'll take a noise source and use instrumentation WX GUI FFT sync. Of course, I'll need a throttle block because I'm doing a pure simulation here. And we always need to throttle our flow graphs if they don't have any connection to any outside hardware like a HRF. Now, we've seen what happens if I just go like this. I just get a flat response. But I'd like to show you what happens if I do something like a moving average. And one way we can do this, if I find my delay block, here we go, it's under miscellaneous, I'll delay the signal by 1 sample. And then I'm going to use an add block, that's under math operators, and add these 2 streams together. Now, to make it a little bit easier to follow, I'll do this all following the throttle block. So I'm taking 1 copy of the signal directly and a second copy of the signal that is delayed by 1 sample. And let's take a look at what that looks like. I'm just adding these 2 together. So in other words, the first and second samples get added together. The second and third samples get added together. The third and fourth samples get added together, and so forth. Now here's what my frequency response looks like. Notice that it's no longer flat all the way across. I actually have a higher frequency response toward the middle and a very poor frequency response out at the edge, at the extremes. In other words, I've created a low-pass filter. It might not look like a very good low-pass filter. The pass band is not very flat, or it's a little hard to tell where the pass band starts and where the stop band ends. I'm not really sure, but there's definitely some stopping here and some passing here in the middle. It looks to me like it has a very wide pass band, but it's not very flat. But it is a low-pass filter, and we implemented it very simply by just averaging 2 samples in a row together, or adding them together. I suppose if I divide it by 2, then it would be a true average, but I've just added them together. Now, let's take a look at what that looks like in a scope plot. If I go into instrumentation WX and use a WX GUI scope sync, then I should be able to see the actual sample values. Now, I'm doing this with complex numbers, which makes it a little bit harder to compare 2 things against each other. So let's take a look at what this looks like if I go with real numbers. I just highlighted everything and then hit the down arrow to convert the data types to real numbers, which makes it to floats, which makes it a real valued signal. Now things will look a little bit different. Let's take a look back at just the FFT sync for a moment. Now we see just the right-hand side, or just the positive frequencies of my flow graph, of the signal, or the frequency domain representation of my signal. Now, if we look at the scope sync, one thing that would be cool to do would be to compare the output of our adder with the input, or the actual original signal. So what I'll do is I'll go into my scope sync, into properties, set the number of inputs to 2. Now I'm going to take the original signal and plug it into one input, and then the modified signal and plug it into the second input. And that gives me a way to directly compare one versus the other. Now I'll run my flow graph, and you can see that the blue line, which is channel 1, and the green line, which is channel 2, do look very similar to each other. And if I stop it for a moment, you can see something interesting. Do you notice how the blue signal just looks a little bit more spiky than the green signal? It has a little bit more high frequency content. Also notice that the green signal lags behind the blue signal just a little bit. You see how there's a peak in the blue and then the green lags behind it? There's a low peak here, and then the green signal lags behind it. Here's a high peak, the green lags behind it. We've added a little bit of delay, but we've also removed some high frequency content. So how can we do a little bit more of this? What can we do to make this into maybe an even better filter? Well, one thing we can do is we can take more delay. If I copy and paste my delay block, I could have a version of my signal that's delayed by 2 samples. And I can add that to my signal. And I'll go into my add block here and tell it to have 3 inputs instead of 2. Now I'm adding the first 3 samples together, and then the next 3 samples, and the next 3 samples. Well, each set of 3 overlaps each other. Let's take a look at how that looks. I'm still doing a simple moving average, but now I'm averaging across 3 samples at a time instead of 2. And we could even go further if we wanted to. Now let's take a look at how this looks in the scope plot. You can see there's still a delay. It's slightly more delay. You might be able to tell that. See the difference from this peak to the next. And the green signal now actually has a little bit less of the high frequency component than it had before in our previous configuration. Let's confirm that by looking at the FFT sync. I'll just look at the FFT for a moment. Look at that. We have, again, I would call this a low pass filter, but we have this pass band down here near 0 hertz, and then we get this really low drop here at, what is that, about 11 kilohertz, a little less than that. And then we go to this section, I would call this the stop band. Notice the stop band is only, the middle of the stop band here is only about 10 dB down from the middle of our pass band. But it's definitely lower. It's 10 dB lower than our pass band. So we have this very distinct stop here, kind of a funny shaped region between our pass band and our stop band. But it is definitely a low pass filter. Now one thing you might want to do is increase the sample rate. If we were to do 1,000,000 samples per second, things go a little bit faster here. But otherwise, it looks exactly the same. Our dip here is at about 1/3 of our sample rate. That's interesting. Now, let's take a look at what happens if we do something a little bit different. Instead of a simple moving average. What if we were to do a weighted moving average? A weighted moving average, we would take, in order to do that, we would need a multiply block, or really I'm going to use a multiply const block, which multiplies a signal by some constant. So if I multiplied this signal by a constant, let's say I multiply it by 1, then that doesn't change it at all. I'll set the data type to float. And let me put a bunch of these in my flow graph here. I'm going to put one into the undelayed signal, and then I'm going to copy and paste that, and I'll move things around so this is a little bit less cluttered. But at my delayed signals, the one that's delayed by 1 will get multiplied by a constant, and the one that's delayed by 2 will get multiplied by a constant. Now I have a weighted moving average. If I were to adjust these 3 constants, I can adjust how much each signal is, each copy of the signal, each delayed version of the signal is weighted versus one another. Right now they're all weighted the same because they're all multiplied by 1. But what if we were to create some sliders? I will use a WX GUI slider and create one. I'm going to call this tap 0. And its default value will be 1, but I'll set its minimum to -1 and its maximum to 1. And then I will make a couple more of these. I'll make tap 1, and I'll make tap 2. And I'll go in here and set this first tap, as I call it, to tap 0. That's the constant that I'm multiplying by. This one is tap 1 because it's delayed by 1. And this one is tap 2. It's delayed by 2. Let's see what this looks like. Now it should look exactly the same as it did before because we have all the taps set to 1. So there's no weighting going on. If I average my FFT plot, you can see that my pass band is 10 dB higher than my stop band. But what happens if I adjust these sliders? Oh, look at that. I can actually change the location of the transition in the frequency domain. I can change the shape of that transition. Look at this. If I set things like so, it looks a little bit reminiscent of when I only had 2 taps here, except I have a longer sort of gradually sloping transition. You might think of it that way. You can change the frequency characteristics, the frequency response of this flow graph by adjusting these taps, or I might call them coefficients. I change the signal. Look at that. I can even create a high pass filter. Just by fiddling with these sliders randomly, I found that I can create a high pass filter instead of a low pass filter. And all we're doing is making a moving average that is weighted, and I'm changing the weighting. And those values, those coefficients of the weighting, I call taps. Now what we've created here is called a finite impulse response filter, or an FIR filter. And you can see that there are FIR filter blocks built into GNU Radio. If you look at in the filters section, one of my favorite blocks is the decimating FIR filter. And we'll talk about decimation at some point, but for now, notice the decimation is set to 1, which means it doesn't actually decimate at all. Now, if you create a filter like this, it asks you for taps. So what do you think we might put as taps there? The taps are, in fact, specified like so. You could type 1, 1, 1, and that would create a 3-tap filter where every coefficient or every tap is 1, which is identical to what we've created in this flow graph here that has multiple delay blocks and multiple multiply const blocks and that add block. In fact, we can compare the results against each other directly. If I change the data type here to float, float to float with real taps, that's what I want. I can go in here and I'll use this scope sync again to compare two signals with each other. Turn off my FFT sync for a moment. Now you can see I have one filter which is specified through all these different blocks, and then a second filter that is specified just with the decimating FIR filter block. If I stop this flow graph, you'll see that there is a blue curve and a green curve, and they look identical to each other except that there is some variation in the delay from one to the other. They're not necessarily synchronized with each other, but you can see that when I feed the same input to these two different filters, then I actually get the same output, the same curve that comes out of it. Let's see what happens if I change the coefficients. Now, I've only set up the coefficients to be used, these taps, to be used in my multiply const block, but I could also set up the same coefficients to be used in my decimating FIR filter. All I have to do is specify parenthesis tap 0, comma tap 1, comma tap 2, close parentheses, and I should be able to adjust my sliders. Oh, something's not working right there. There we go. Adjust my sliders, and the characteristics of the filter may change, but one filter always produces the same output as the other filter with a slightly different delay. Here we go. Now this is easier to see, I think, if you look at the frequency response of the FFT, which we already did. But the key point I want to make here is that the decimating FIR filter does exactly what we have done in this section of the flow graph. It takes multiple copies of the signal, delayed by different amounts, scales each one by multiplying it, and then adds the result together. It's called a multiply accumulate operation. Multiply accumulate means we do some multiplications and then we add up the result of that multiplication. Now clearly we could keep going. We could add more taps if we wanted to. And if we did, consider how much more processing power would be required to do all those extra multiplies and adds. Every single time we add a tap, we add another multiply and another add per sample. Every single time there's a sample, there are multiplies and adds that are a multiple of the number of samples that we have and the number of taps. So the more taps we add, the more CPU power gets used. Now the low-pass filter block that we used in the previous homework is actually an FIR filter. But here's the difference. Instead of specifying taps, what we specify with the low-pass filter block is a cutoff frequency and a transition width. Now, I'm going to ask you in the homework for today's lesson to experiment with different taps and see if you can produce filters that have differing frequency responses. But you don't necessarily have to do that most of the time. When you're working with GNU Radio, you can use this low-pass filter block in GNU Radio Companion and just specify the frequency you want and the transition width you want, and it computes taps for you. In other words, it designs your filter for you. Instead of having to come up with what those coefficients are, you can have this block design your coefficients for you, or determine your coefficients, and that's called filter design. So we'll play a little bit with filter design, but the good news is you don't need to be an expert in filter design. You just need to know a little bit about how the filters work internally. And this is what we've done in this flow graph demonstrates that very clearly. The term finite impulse response means that an impulse, or any sample, any one sample that goes into your filter, has an effect on the output only for a finite period of time, a finite number of samples. And you can see here, there's one sample, a delay of 1, and then a delay of 2. So there are only 3 output samples that can be affected by any one input sample. Those 3 output samples happen, and then it's over. There's no additional effect, long-term effect of any input sample beyond those 3 output samples. So since it's only 3, that's a finite number. We call it a finite impulse response. And the way that finite impulse response filters are implemented is with this multiply accumulate operation. It's also called convolution. Convolution is the name of this operation of doing multiply accumulate across multiple delayed versions of a signal. And the one thing that you might notice is that the low-pass filter block, although it gives you the ability to specify the cutoff frequency and the transition width, it doesn't actually tell you what the taps are. And that's why I had you do that part of the exercise in the homework for Lesson 9 to take a look at your CPU utilization, because something you should learn there is that when your cutoff frequency, and especially when your transition width, is very low in comparison to your sample rate, your CPU utilization goes through the roof. The reason for that is because in order to achieve such a sharp transition, it has to compute a large number of taps. So the tighter your filter is, the more taps it uses, and that's why the CPU utilization goes up. No filter is perfect, and that's why you should always test your filters, whether you design the filter yourself or let GNU Radio design the filter for you. You should test the frequency response of a filter that you're going to use. FIR filters, or FIR filters, have a trade-off that we've observed between the sharpness of the frequency response and the amount of computation required to implement the filter. And other types of filters have similar trade-offs. Even analog filters have trade-offs. An analog RF filter circuit is it doesn't have any computation involved, but it does have a trade-off between the sharpness of the frequency response and things like the size and the cost of the circuitry. And we've talked about in Lesson 9 anti-aliasing filters. Anti-aliasing filters in a software-defined radio receiver allow the intended frequencies to pass into the digital domain and avoid aliases from other frequencies to go into the digital domain. And similar things happen during transmit. And I'd like to take a minute to show you the effect of the anti-aliasing baseband filter in HRF1. I'm using Osmocom FFT just like I did in Lesson 9, and I have that car key again, the remote keyless entry device. So if I press the button on the car key, you can see the transmission show up. I'll turn on peak hold here, and I want to show you something about the shape of the analog baseband filter. That's the anti-aliasing filter in HRF. Now, one thing to notice here is that my sample rate is set to 10 million samples per second, and the bandwidth setting is set to 7.25 megahertz. That is actually the configuration for the analog baseband filter, the anti-aliasing filter. And if you look, if I turn on averaging, for example, if I turn on averaging, you can kind of see how the noise floor tapers off at either edge. Over here above 7.25 megahertz above my center frequency, you can see that there's this sloping, downward sloping noise floor, and you can see the same thing on the negative side. But the noise floor isn't necessarily the best way to observe the analog baseband filter because the noise level is fairly low, and some of the noise comes through the antenna, but some of it originates within the HRF itself in different stages. So the best way to observe the performance of the filter is actually by doing peak hold like this. Now I'll push the button on the remote, and now I'm going to advance my tuning frequency. I'll just go up to 315 megahertz instead of 314. And now notice the peak still stays where it was on the screen, even though I've actually shifted frequencies out from under it. So if I push the button again on the remote, now you can see it's shifted down by a megahertz. Now the frequency of the remote hasn't actually changed, it's just that the frequency here that I'm tuned to has changed. If I go another 1 megahertz, and then another, and then another, now we should be getting around the edge of the filter. Notice how this one was slightly less in amplitude than these. The power level is down, should be about 3 dB if we're right at the edge of the filter, because normally filter bandwidths are specified by their 3 dB point. Did I do 319 yet? There it is. Now look at that. I went another megahertz up, which causes this peak to shift down 1 megahertz, which goes off the bottom of off the side of the screen and onto this side. This is aliasing. We're seeing this peak show up here close to 324 megahertz, but we know that it really wasn't at 324 megahertz. It was actually just below 314 megahertz. But since our sample rate is set to 10 megahertz, we see it show up as an alias on the other side of the screen. However, look at the power level. It's a good 10 or 12 dB less than the peak was when it was actually within our filter bandwidth. But like I said, no filter is perfect. If we keep going higher, 320 megahertz, now we see this. Look how much just shifting 1 megahertz caused an additional 10 dB of power to go away. I'll go up again and maybe you'll be able to see it, but it's getting really low down here. But this shows you that aliases happen. Aliases, even though we have anti-aliasing filter in our FDR receivers, an anti-aliasing filter isn't perfect. And depending on what this bandwidth setting is, how this is configured, you may get more or less of this aliasing from nearby frequencies that shows up leaking into the edge of your captured bandwidth. Let's try this exercise again, but let's do it with a different bandwidth setting. I'll turn off my peak hold, and I'm going to change my bandwidth setting. I'm going to reduce it down to, say, 2.75 megahertz. Now again, if I turn on averaging, you can actually see that. You see how this little hump in the middle of the noise floor shows up? You may or may not be able to see that depending on the particular circumstances of your capture, but what you'll definitely be able to see is the effect of that baseband filter when you have an actual strong signal. If I turn on peak hold and start my transmitter, and then I go up 1 megahertz and I start my transmitter, you can see that it was about the same power level there. If I go up another megahertz, now look at that. The power level drops off dramatically. I'll keep going up and up. Look at that. At 318 megahertz, I'm only off by 4 megahertz approximately from where my signal of interest was, and I'm not picking it up at all. I should be seeing a little peak right about here where my mouse cursor is, but I'm not really seeing anything at all because this filter is much tighter. It has a bandwidth of 2.75 megahertz instead of a bandwidth of 7.25 megahertz. And so we have the ability to change or configure the bandwidth within certain limits. The narrowest we can make it with HRF1 is 1.7 megahertz, and the widest we can make it is actually, well, it's much wider than our sample rate, in fact. And so we have the ability to control those aliases to different degrees. In general, in order to get the highest quality signal with the lowest amount of unintentional aliases, the thing to do is to make the bandwidth setting as low as possible. That's the analog baseband filter. Make it as low as you can get away with but still capture your whole signal of interest. And then increase your sample rate as much as you're able to. Now that incurs a cost in CPU utilization, but the wider you can make your capture bandwidth compared to your analog filter bandwidth, the cleaner a signal you're going to get, and the less aliasing will be introduced into your digitized signal. Now I'd like to take a look back at the homework from Lesson 9 and continue to look at the effect of different filters. We've seen how a low-pass filter looks. Now let's take a look at what high-pass and band-pass filters look like. So if I put a high-pass filter into my flow graph, I will just delete this low-pass filter for now, and I will configure my high-pass filter to have the same parameters, cutoff and transition, which are my sliders. If I take a look at the frequency response of this flow graph, you can see that my cutoff frequency is now the lower edge of my pass band. If I hit my average here, you can see this a little bit more distinctly. My cutoff frequency is around 125 kilohertz. There it is. And then below that, we see this transition width. If I make the transition width narrower, then you can see that it's a sharper edge to the filter. Now this might look a little bit funny at first, and for that matter the low-pass filter might have looked a little bit funny at first if you weren't used to thinking about signals in as complex valued signals and what that means for the frequency domain. A high-pass filter passes signals that are high in the positive direction and also high in the negative direction. So in some sense, this actually looks sort of like a band pass. If you imagine that this frequency domain is cylindrical, remember that it's periodic. So if you go off one edge of the plot, you come around the other edge. So in that cylinder, depending on how you look at it, this might look like a band pass filter or a band stop filter, where we're stopping this band right here. If I change my cutoff frequency, if I make it very high, close to half my sample rate, now you can see I'm only passing these signals that are, or the portion of the signal that is at frequencies well above 400 kilohertz here, or below negative 400 kilohertz, which is getting close to half our sample rate. Now, if I take a look at a bandpass filter, I will, not a band reject filter, but a bandpass filter, and plug that in here. I'll just disable my high pass filter for now. I can set this to cutoff and transition, but now I have this separate parameter, cutoff. I'll call it high cut, but I don't have that slider yet, so I'll create a new slider, copy and paste. My new slider will be called high cut, and I'll give it a default value of, let's say, sample rate over 4 instead of sample rate over 8. Let's take a look at what that looks like. Here we go. Now, this is my bandpass filter, and you might have imagined things as being just one band, but you can see we actually have two bands, some positive frequencies and some negative frequencies. And this is a consequence of having complex valued signals. So this particular filter might not be very useful, because most likely your signals of interest are going to be all together, not in two separate frequency bands. So if your signals are all together in one, it would be nice to be able to specify a single band that you want instead of what we have here, which is mirror image bands. But it's interesting to move these around. I can change my cutoff frequency. If I make my cutoff very low and my transition very low, you can see I can get pretty close to 0 hertz there. I can make my high cut higher. I can move these around, but no matter what I do, they're always these mirror images, these two mounds that are mirror images of each other. Now there is a way to specify a filter that has only one of these lobes instead of the other. And the way to do that is to, and in order to do that, we have to describe a frequency domain that is asymmetric. The negative frequencies are different than the positive frequencies. So how do we describe a signal? How do we make a signal capable of describing both positive and negative frequencies and have them be different from each other? Well, the way we do that is with complex numbers, of course. So what we can do is actually change our block. Instead of having real valued taps, we can change it to have complex valued taps. Now the default for all of these blocks, the bandpass, high pass, and low pass filter blocks, the default, if you look in the FIR type, is to have complex input to complex output with real taps. If we go complex input to complex output with complex taps down here, then things look a little bit different. Check this out. This looks maybe more like what you would expect when you hear bandpass sample, or sorry, bandpass filter. You would expect to see one pass band. Now I can set my cutoff wherever I want, I can set my high cut wherever I want, I can set my transition width, but notice I have things configured not to allow me to set these to negatives, but I can set them to negative now because I have complex valued taps. I can go in to my sliders and I could set my cutoff here. I could set the minimum, instead of being very close to 0, let's set the minimum to negative sample rate over 2. And let's set the high cut also to have a minimum of negative samp underscore rate over 2. Now let's take a look at what that looks like. Now I can set my cutoff frequency below 0 if I want to. And I can arbitrarily select any band that is within the bandwidth described in the digital domain by this digital signal. Anything we want, we can set it to. And we can choose a wide transition or a narrow transition and pick out whatever region of the frequency domain we're interested in. FIR filters are not the only types of filters we use in software-defined radio, but they're among the most popular. They can be implemented very efficiently in digital logic, for example in an FPGA, and they can be optimized quite well with vector instructions or SIMD instructions on a general-purpose CPU, and that is in fact how they're implemented by GNU Radio under the hood. Now, the thing that I like the most about FIR filters is how flexible they are. You can implement a filter with whatever frequency response you want simply by changing the coefficients. And I'd like you to explore those coefficients a little bit more in the homework for this lesson. Go to greatscottgadgets.com/SDR to view the homework assignment for Lesson 10. I hope I'll see you next time for Lesson 11.